We are looking at our third week of AP Chemistry review. Better late than never. So hopefully you've been following along and you've been working week by week as we get closer to the AP exam in 2022. Tonight we are going to be looking at intermolecular forces and properties. And oh man, is this unit a doozy. All right, so as you can tell, this unit is jam-packed. There it shows 13 different topics that are contained in this unit. And if you look at the top up here, it's going to tell you that this part of the test is a large portion of the material, right? It says 14, 15 class periods, but it's 18 to 22% of the AP exam. So this is pretty hefty compared to the time they expect you to learn it. So even this first topic, intermolecular forces, I see lots of students struggling with that for weeks. And some of these other ones kind of just sneak in along the way. It's also got ideal gas law in here. It's got solutions and mixtures, lab separations, spectroscopy, the electromagnetic spectrum, the photoelectric effect, the Lambert Law. So you can tell there's like a lot going on here in this unit. So yeah, we're going to try to cover all of it, basically the best that we can. And of course, if you're following along at home, if there is parts of this that you don't want to see the whole thing, we'll post a recording later with chapters and all that. But if there's something like you're like, whoa, I wish I really knew more about deviations from ideal gas law, then let me know and I can make a video more detailed on that, because obviously there's only so much I can say when I'm covering this many topics and trying to keep it somewhat succinct. All right, so let's get started. Our first topic tonight is intermolecular forces, and this is probably the biggest one that we're going to have to talk about. These are inter. What does that mean? Like an intersection. It's not the same as intra. No. It's not intra. It's intermolecular forces. So these are not forces inside of a molecule like the covalent bonds of water. No, it's not that. It's in fact the interactions that water molecules have between each other. Okay, so intermolecular forces. These are the forces between molecules. And typically we can rank them as follows. Now, some students, their teachers might not mention ion at the top. And, they're like, oh, isn't that intramolecular? It's like in a compound. That is true. But I like to put it on here. It helps me think about how all these are related. And below that would be ion dipole. And you're not usually going to experience that if you have a pure substance. But if you're, say, mixing something in water, yeah, there's definitely going to be ion dipoles there. Right below that is going to be our special type of dipole-dipole, which is a hydrogen bond. Then we've got the dipole-dipole. And finally, at the bottom here, we have a London dispersion forces. Okay, and let's see how this works. London dispersion forces, everybody. This is like the people's IMF. Like everybody gets this one, right? Like every single type of molecule has London dispersion forces. Dipole-dipole is going to kind of be limited to polar molecules. Hydrogen bonds are nothing special. They're just dipole-dipole bonds with some that are really, really strong. And we'll get into that in a little bit. So this is essentially polar with either oxygen, nitrogen, or fluorine bonded to hydrogen. Ion dipole, that's going to be between an actual ion, like a sodium ion, and a dipole, a polar molecule like water. And then, of course, ion is going to be based on the attraction and between ions of different charges. So if you have trouble determining intermolecular forces, sometimes a flow chart like this may be helpful. Obviously, you can't use it on the AP exam or in your teacher's test, but when you're practicing at first, this can kind of help you think about it. And eventually, hopefully, you kind of internalize this flow chart. So most of the time, if you are essentially not thinking about ionic compounds or mixtures and more of a pure substance, you can almost start right here. But we can start at the top to see. So the first thing you want to ask is it interacting molecules or is it ions involved? And if ions are involved, we're going to take this path and it's going to guide you down to see that if it's polar molecules and ions, it's going to be ion dipole forces. And if it's ions and ions, it's going to be ionic bonding, which we've talked about in the past. Now, this is the more common pathway that we take. It's not involving ions. And the first question we ask ourselves, are these molecules polar? So, I see a comment. If I have time, would I mind doing an AP environmental science review? That's not my specialty, so it's probably a little bit below my AP biology videos that I want to make too. But if I have enough time, I will see what I can do with there. And maybe at least like a tips and tricks and tips as opposed to a full on video dedicated to environmental science. But back to this intermolecular forces. We're going to ask ourselves, are polar molecules involved? And if the answer is no, we're going to go straight to London dispersion forces. And poor old non-polar molecules, that's all they get is London dispersion forces. Meanwhile, if there is polar molecules, you can have this dipole-dipole interaction, or you could have hydrogen bonding, and we'll get into these details in just a minute. Now, all three of these are considered van der Waals forces. Be careful. A lot of teachers say that van der Waals forces and London dispersion forces is the same thing, when in fact, it's just a type of van der Waals force. I would just stay away from this whole term in general. I see this so inconsistently across the entire internet, across textbooks of what's a van der Waals force and isn't. From what I know, it's anything that's not a permanent full charge like an ion. So any of these would count, including induced dipoles. The AP exam explicitly states that London dispersion forces and van der Waals forces should not be used interchangeably. So I just like to stay away from it in general, but let's move on. Okay, so the first one we're going to talk about is ion. That's basically an ionic compound, right? NaCl, and it's probably bonded to some more Cls and some more Nas. These are the electrostatic interactions between these. And I know it's an ionic bond, isn't it the same thing? And yeah, it essentially is, but I don't want to say an ionic bond isn't a bond, but it's not a sharing of electrons. That's for dang sure. It's a attraction between ions. And this is going to be super, super strong, a very, very powerful intermolecular force. So typically, ionic compounds like NaCl have very, very, very high boiling points, right? You don't just throw a bunch of salt into a pan and start boiling it up. It's going to take a lot of heat. You're probably going to blow up your kitchen. Don't do that. Don't boil salt. The other one I want to mention, and again, this is going to more apply to more like to solubility and things like that, which we'll talk about tonight as well. But ion dipole interactions is when you have polar molecules and ions in solution. So this essentially explains why something like sodium chloride is going to dissolve in water. There is an attraction between the partially negative charge on oxygen. And if you're not sure about why there's a partially negative charge on oxygen, go back and watch last week. We talked about polarity. So there's an uneven distribution of electrons, and that partially negative region right here is going to be experiencing attraction to the positive charge. And as these waters kind of sneak in there and surround sodium, they break it up from chlorine. So these polar molecules can lead to things dissolving in the first place. All right, now the ones that everyone wants to talk about, which is the dipole-dipole interaction. Like, what even is a dipole? Well, dipole is just this concept that there's a slight polarity in the molecule, that there is one side that's a little bit more positive because it's not so strong in terms of electronegativity, and the other side's much more electronegative. It's going to be greedy for those electrons, yanking on those electrons. So when one HCl meets another HCl or another polar molecule, of course, this slight negative charge is going to be attracted to this slight positive charge, and they're just going to be lining up all day and in 3 dimensions. So hopefully you can kind of see how these dipole-dipole interactions work. Oh, thank you. Whoever you are, Horsey Pony, thank you for your support. I'm glad that somebody's out there watching this, and I'm not just making these for myself. But even if that was the case, heck, I really like chemistry, so this is kind of fun for me. All right, so we see some attraction going on here. That's a dipole-dipole. Now, there is such a thing as an induced dipole. That's when you kind of got like a non-polar molecule off to the side, and the polarity can actually pull electrons to one side. Not going to go too much into that today. Now, it's like a special edition of dipole-dipole, and those are called hydrogen bonds. They are not real bonds. We talked about this last week. They are the imposter bond. It's not like a James Bond thing either. They're not real bonds. They are intermolecular forces, and they're basically just dipole-dipole on steroids. They're super buff. And why is that the case? Well, because oxygen or nitrogen or fluorine, these are usually the 3 elements we consider create hydrogen bonds. They are so electronegative. Remember, they're in the very top corner, in the electronegative corner of the periodic table. That they are going to really yank on those negative electrons and really leave a positive charge on hydrogen. So these bonds between the negative and positive areas in the water molecules are going to generate these hydrogen bonds, and they're very strong. They're the strongest type of dipole bond. Now be careful. Don't just think because you have any molecule that, say, has an oxygen over here and has some hydrogens over here. I guess we could do something like that. That's not necessarily going to be hydrogen bonding. It has to be the hydrogen is bonded to the oxygen, nitrogen, or fluorine. So don't get that twisted. Okay, the last one we want to talk about is London dispersion force. And this one, everybody has it. You're like, oh, it can't be that great. Everyone has it. Well, that doesn't mean it's not great. It's just maybe it's so popular. That's why all the atoms want to have it. But let's look at a non-polar molecule. So we're going to look at methane. If you, again, are confused about polarity, go back and watch last week's video where we talked about that a little bit. So we do know that they're supposed to be sharing the electrons. And when we first learned this, probably in middle school, we're like, oh, they're just like locked into place. But that's not the case. These electrons are actually being shared all throughout the molecule. They're dancing all the way around here, since none of it's that more electronegative than another. I guess carbon's a little more electronegative. They're like flying all around. But in any random moment, if I just said pause, there is a chance that maybe I got a little bit more electrons on one side than the other. So it's like a momentary fleeting polarity. So this, for this slight moment, it's going to be a little bit more negative and a little bit more positive. Now, if you had another CH4 molecule and it was also doing its kind of random thing, again, randomly, but if that had this moment of positive charge, there's a chance that it's probably going to attract a little more electrons over there. So there'll be another little moment of positive charge. Oh gosh. Vincent. All right. I'm glad that you are getting the help that you need. I think I remember who you are. I've known a few Vincents in my day. So we have some kind of interaction here that's kind of like fleeting, it's passing, but this is London dispersion force. It's built on these kind of slight moments of just localized electrons where they're on one side a little bit more than the other, and that generates these London dispersion forces. Now, why am I mentioning them if they're the weakest ones? Like, they're not that important, right? Well, I want to use a quick analogy with you, and this is what I call the 5 cents, $5 analogy. And this is the idea that eventually these London dispersion forces can add up. So if you get a really big molecule, like everyone's talking about gas these days because it's expensive, apparently. That's why you should probably just ride a bike everywhere. If it's possible. So we're going to draw this big old monster molecule. This is going to be an octane molecule. Here we go. Here we go. Right, there's a lot of hydrogens here. So this one's like pretty massive. And if you watch my last video, I told you always remember that the CH bond is considered nonpolar. So this is a very nonpolar molecule, and it's still got that random movement of electrons. They're all sharing the electrons. And when you have a bigger molecule, at any moment, if I just said pause, there's a higher probability that there's an uneven distribution of the negative and positive charge, just because it's larger, just because there's more electrons. And we call this concept polarizability. The larger the molecule, the more electrons and the more surface area that's present, the more polarizable that molecule is going to be, which means it can have potentially a greater LDF. Now, LDF is like a little nickel over here. It's like a 5 cent kind of thing. And hydrogen bonding, let's say that this is like a $5 bill. Well, heck, anyone who's been a little kid and saved money in their piggy bank, or maybe even been an adult and picking up coins off the ground or recycling cans or something, is going to know that if you have enough nickels, you are going to eventually have more than $5. So that's why a particle like octane, a molecule like octane, actually has stronger intermolecular forces overall than a molecule like methanol, which has this OH group. And you're like, dude, that's hydrogen bonding. I thought that was like the king of the van der Waals forces. And it is, but sometimes you got enough nickels, you can buy whatever you want. So I want you to know this idea of polarizability. Now, there's usually this moment of panic that comes in for most students when they realize there's like this other factor of polarizability, and they're like, how am I going to know? How many carbons does it take before that nonpolar molecule is stronger than the hydrogen bonding? How am I going to do that? And they aren't going to ask you something like that point blank. They're not going to give you a borderline case on the AP exam, or even your teacher, unless they're a sadist. They're not going to do that. What they will do, and this is one of my advices of the day, is, which the advice of the day is don't fight the data. Okay, and you're like, what does that mean? What do you mean don't fight the data? So what they like to do is say, hey, so we looked at the boiling point of this and it's like 200 degrees. I'm just making it up off the top of my head. I don't think that's true. But, and then maybe this one, the boiling point's like 70 degrees. And they're like, explain. And if you try to fight the data and say, oh, there's an anomaly in the data, your thermometer's broken and your sample of methanol is tainted, and right, you don't want to, that's not what we're trying to say. That's like the cheap cop out when you don't know why your lab went wrong and you just start blaming it that the scale was broken and somehow someone gave you a bad graduated cylinder. No, we don't want to fight the data. They're asking you that question because they want you to bring up polarizability. So they won't ask you flat up like which has more IMFs, but they might say, hey, this one has these boiling point really high. This one has this boiling point really low. How can you explain that? And that's where you bring in this concept of polarizability. So in general, we can still follow this as our ranking system of the strongest is ion-ion, goes down to ion-dipole, hydrogen bond, dipole-dipole, and London dispersion forces. However, London dispersion forces can kind of add up if the molecule is large enough, if it's polarizable enough, and it will overcome some of these other ones. Again, you're not expected to be able to predict that without some kind of table or chart, but you should be able to explain why one might have higher values than the other. Okay. So this is my own creation. I hope you find it funny. So why am I even talking about IMFs for almost 20 minutes if I'm trying to talk about 13 different concepts today? All right, because it's really important at connecting the microscopic world of chemistry with the macroscopic world of chemistry, the little stuff to the big stuff. And the bridge here is IMFs. It's not atomic. It's not big physical properties. It's explaining how the molecules are interacting. So usually when you have greater IMFs, when your IMFs are large, what is that going to mean? That means that you're going to have a higher melting point, a higher boiling point, right? And if you think about what you understand of how molecules interact, that makes sense. When they're in a liquid, they're all kind of attracted to each other. They're all interacting a little bit. If you want to turn them into a gas where they're just like, whew, we're free. And that's the next topic we're going to talk about is gases and liquids and stuff. So if you want to get them to that point, you've got to overcome those intermolecular forces that they're having, that attraction that they're having, whether it's LDF or dipole-dipole or ionic bonding, whatever it is. To overcome those, you have to add energy. So it would make sense that the boiling point is higher. You got to add a lot more heat. Same thing with melting point. Also, something called surface tension, which is like why water beads up and why some bugs can walk on water. Water has a lot of surface tension because there's a lot of intermolecular force. And it essentially is an attraction across the top of a liquid, that top layer, and it can almost make it like almost like a solid surface substance. Another one is viscosity. Viscosity is like a liquid, how it pours. Like syrup has a very high viscosity because it's very polar. It has a lot of intermolecular force and it doesn't flow very easily. So all of these are going to increase when you have larger IMFs. So they love to ask you these questions. They won't just straight up ask you which one has the greatest IMFs. And AP even warns, don't just use this has strong and weak IMFs. You should be able to identify them. So if it's a short answer, a free response question, and you just say, well, that one has more, they're probably not going to give it to you. But essentially, all of these physical properties correspond to the strength of the IMFs. Now, the one that's like the weird odd man out, where if you're looking over there at my weird Spider-Man meme, maybe you're starting to figure out, is vapor pressure. And that's not because of some crazy thing about IMFs. That just has to do with the definition of vapor pressure, right? It has to do with how much of the molecules are going to be exiting the liquid phase, even if it's momentarily, and entering the gas phase at a certain temperature. So again, the tighter that all these molecules are holding on to each other, they're not going to let one guy who's got some mission to Mars in his brain jump up and become a gas for a moment. The stronger those IMFs, the harder it's going to be to jump out of the liquid phase and into the gas phase. So practice IMFs. You should be able to identify melting points, boiling points, surface tensions, vapor pressures, just the same way that you did with atomic radii, ionization energy, and all that other stuff from the periodic trends video. Remember, vapor pressure is the odd man out. So that's the one that is opposite of everything else, but everything else is directly proportional to IMFs. So again, if you're really having trouble with this, practice, look up some molecules, look up some practice problems, maybe use this flow chart to get started. And then as you start to get some momentum, you're going to see sort of like when to identify each one and how it connects to the different strings. Okay, so jumping ahead, trying to get through everything today, is the properties of solids. So we alluded a little bit to this last week when we were talking about ionic compounds and covalent compounds. I'm not going to really go through all of these. If this is something you don't get and you need help going over it, pause the video right now and kind of look at this chart. Again, I really love charts, and I don't like just finding them online. It's really powerful to make them yourself, because you have to ask yourself, well, what's the important stuff I should know? Go back in your notes. Oh, maybe it's, what do we call those particles? What kind of forces do they have between them? Are they hard or soft? What's the melting point like? What's the solubility like? What's the electroconductivity like? Is it bendable? Is it malleable? And you have to think, what are the interesting properties? Maybe you might put in a thing over here that says examples, so you can kind of remember. I can give you some examples too as we go through it now. So an example of something molecular is CO2. This is going to be anything that is covalently bonded. I could list these all day long. O2, NH3, and they can be big boys too. They could be like a some kind of hydrocarbon or something like that. And in general, these molecules do not have that strong of intermolecular forces. They may have dipole-dipole or even hydrogen bonding, which is going to add a little bit more strength. But in general, they're relatively weak towards these, compared to these other bonds, which are intramolecular forces, which are much stronger. We have metallic substances. They feature metallic bonding, the sea of electrons thing. And they got high melting points. They are very electrically conductive because of the ability for electrons to flow through them. And they're very malleable because of their overall structure is that sea of electrons. So they can kind of have their sheets of positive, planes of positive protons, nuclei kind of slide past one another. Now, ionic compounds, we've talked about those last time. Again, they are very conductive when they're molten or they're in solution, not when they're a solid, hard substance. In fact, they're not going to conduct very much electricity at all, because the ions are like all busy locked into shape with the other ones. They don't have a chance to kind of allow the electrons to flow. And finally, we have covalent network 3D. Or there's 2D networks of it as well. But covalent network solids in general, you're usually going to see them between Si or carbon. And these things are just gigantic molecules, right? Like carbon can make 4 bonds, and it can make the next one 4 bonds, and it can make with the next one 4 bonds, and so on and so forth. And there's some different geometries that can form. Diamond, for example, is like this really kind of perfect tetrahedral repeating pattern, and it makes for a very, very hard, very strong substance. In general, covalent network solids, although they seem molecular because they're covalent, because they have so many covalent bonds, they actually, how would we say? They actually are much harder, higher boiling points. They don't like to break down, essentially. So again, make the table for yourself. Find a cool table like this one. Whatever it takes, you should be able to identify these pretty easily at this point in the course. All right, solids, liquids, and gases. We're only going to talk about this real quick. This is stuff you should know from like middle school, right? You've been learning about, I feel like I learned this in like 2nd grade, to be honest, solid, liquid, and gas. And I was trying to tell everyone I heard about plasma. I came up with the new thing. But if you notice up here, it does say understanding interpreting phase diagrams is not assessed on the AP exam. So that's that like triple point thing, right? It's not on the, if I don't even know what that looks like, it's not on the AP exam anymore. They say that that's because it's prior knowledge. You should already know that before AP Chem. Okay, it doesn't really matter the reason why, but essentially that's not on there. What you should know, right? Solids are rigid, fixed shape, fixed volume. Liquids, a little bit looser. They have no fixed shape. They kind of spill everywhere, but they still do have a fixed volume. And then gas is essentially, they're just, the particles are really far apart and they're moving really, really fast. And the properties of these, again, can be defined by intermolecular forces and polarity. In a solid, the intermolecular forces are very strong. And as you add more energy and more heat, right, energy would be getting these molecules to vibrate and jump around from each other. They are going to be harder to maintain those intermolecular forces because now they have more kinetic energy and they start to kind of break away. And eventually with a gas, that's when it's sort of just liberated itself completely. Okay. Real quick, I'll just mention this for the sake of completion. These are phase changes. We'll talk more about it when we get to thermochemistry, but you should know the basics. Most of these I think you probably know, like condensation and vaporization, melting and freezing. These are two that not everyone knows about, but they're pretty cool. That's when solid goes to gas or gas goes to solid. So check those out. Sublimation and deposition. Usually they use this one is like iodine crystals, and sublimation, a really good example is dry ice, right? You go to someone's house and they have like that foaming witch's cauldron for like a Halloween party. That's sublimation. That's solid CO2 becoming gaseous CO2 and kind of trapping some water particles in it in the mix and giving it that foggy, steamy look. Finally, there is some other weird forms of matter. The most common is probably plasma. That's where it's so much energy that the electrons and nucleus are sort of separating from one another. And there are, of course, other exotic ones if you want to learn about it, but it's not in the scope of this exam. So moving forward, and this is why this unit is just like an absolute beast, is there's so many different things in here. Now it makes sense why it's 20% of the test. So our next topic is the ideal gas law. Okay, PV nerd. This should be like your best friend by now. If you didn't take a chemistry class before AP Chem, then you didn't get as many fun opportunities to use this equation, but you should have done at least a little bit of practice with it. So do know that they stand for pressure, volume, moles, the gas constant, and temperature. You're like, dude, they give me this on the formula sheet. Yes, it's true, but make sure you know how kind of the tips and tricks, so to speak. So the gas constant, I usually just like to do everything in atmospheres, and that usually is the best case for gases, but there are some other units too, so you should be familiar with pascals. Let's see what else. Torr. These are just some other ways of measuring pressure. So just be familiar with that. The gas constant is usually used for gas law stuff, is like the atmospheric one. But later on in the course, when you get into like thermodynamic stuff and equilibrium stuff, there's another equation that involves R. And because it's involving joules, and joules is like more SI unit, than the SI unit that goes with it is pascals. So just be careful of when you choose to use R. The other thing, the big trick with temperature is this needs to be in Kelvin, and they rarely give it to you in Kelvin. They usually give it to you in Celsius. It would help if I could spell things right. Okay, so in Kelvin, make sure you always do that conversion. But I would say more important than knowing how to just use the law, because they don't give that many questions where they just go, oh, this is the pressure, this is the temperature, calculate the moles. On a good day, they do. But a lot of times they ask you weird questions like, oh, a balloon started floating high in the sky and the pressure was much lower there. And so was and then what would that do to the volume? So in general, you should know how to use these equations to kind of guide you home on these kind of conceptual questions. If two things are on the same side of the equation, that means as one goes down, the other is going to have to go up. They're inversely proportional. If this is going to stay constant, they're going to have to adjust in order to do that. So more than even being able to do the calculation, know how to use these equations and understand the relationships, right? Like if pressure goes up and everything else is staying constant, then temperature is going to have to go up too. That's the only way that we can maintain the equality. Okay, so PV nerd can also be extended. The ideal gas law can also be extended to and basically turned into things like Dalton's law of partial pressures. And you can derive this from this law based on like moles and stuff like that. Also, this guy, I love this guy. This is like the combined gas law. So you don't need to memorize who's Charles and Boyle and all those guys. It's really great. I mean, I'm happy that they made the contributions to science that they did, but you don't need to know who's who and which law is which. If you know this law, it kind of combines a lot of the other ones. So this law is usually more useful when you have like a change in state, like you have pressure and volume and at one temperature, and what's the new pressure and volume at a different temperature. PV nerd is usually better for like a specific situation. Also in gases in general, this is like this amazing place that they love to throw. I don't think it's amazing, but they'll just throw it in there and connect it to basically whatever other part of chemistry that they want, right? It's like an FRQ. It's all about like solutions or something. And then they ask you like a random question related to gases. And that's because there's a lot of variables here that allow you to connect to other things, right? We got temperature that could technically pull us into some thermodynamic land. Moles. Oh, this is stoichiometry, right? So now we can pull and connect this to stoichiometry. There's lots of gas stoichiometry. This will, like I said, can be connected to thermo and other things related to that. Volume. Volume can be connected to density. It can also be connected to things like molarity. And pressure, when you get into those equilibrium unit, pressure can also be a substitute for, or a way, not a substitute, but a way to represent concentration. So a lot of the equilibrium laws can work using pressure. So just know that the gas law, it connects a lot of concepts. It's often like this weird, it might feel like it's not connected to the problem, but it allows like a lot of concepts to be linked up with one another. Something else they love to put on the AP exam. So if this scares you, you need to overcome that fear. Are the relationships between? So you might notice that, hey, temperature and pressure at constant N and V, right? PV equals nRT. As pressure goes up, temperature goes up. Hey, so that's a direct relationship. As pressure goes up, volume goes down. That's an inverse relationship. Graph looks like that. Sometimes they get weird on you, and instead of putting pressure in volume like this one, they give you something like that, 1 over pressure. And then that's still showing an inverse relationship, but the graph actually ends up being a linear line. So be familiar with these, be able to look at a graph and know what it's trying to say. This is explicitly stated in the College Board outline of the course, is that you should be able to know the graphs that are related to the ideal gas law. Okay, moving on. We are at kinetic molecular theory. So KMT, what is it? Before we can know how to use it and what it is connected to, we want to know what it is. So there's some different versions on there. I think this one's pretty thorough in terms of these 5 assumptions, which is that gas particles are in constant, random, straight line motion. Particles are separated by very great distances. Collisions are rapid and elastic. No force exists between particles, and by that it means like intermolecular forces that we talked about earlier. Like, dude, you taught me all that stuff about intermolecular forces, and then we're going to assume they don't exist. Yeah, that's basically what we do for gases. And then the total energy of the system remains constant, unless they had told us something. But we're going to assume that all those collisions with the sides of the container are not generating heat that's escaping. So these are a lot of assumptions. These are not actual real gases, but they allow us to make a lot of predictions and to explain a lot of things. So scientists use this simplified model to essentially explain a lot of things related to gases. Okay, so from there, from kinetic molecular theory, well, it's really based on this idea here of kinetic energy. We can extrapolate it and connect it to a lot of other concepts that get connected to gases. So first thing we want to go over is, what is temperature? Right? You're like, oh, temperature is how hot it is. Sort of. Temperature is the average kinetic energy. So that doesn't mean every particle that's at 100 degrees Celsius has the same kinetic energy, but it means the average kinetic energy. And this is going to be an important concept kind of throughout the course, the rest of the way, thermochemistry, but especially with gases. So you should be familiar with this kinetic energy law. They give it to you on the formula sheet, but it's able to be kind of manipulated into a lot of different other formulas. So one way that it can be kind of manipulated and changed is if you assume that the temperature is constant, which means the average kinetic energy is constant, then you can essentially derive this, if the kinetic energy is constant, this formula here. And you're like, what the heck does that mean? And essentially it's just saying that the rate, or the speed, the rate of diffusion, so how fast a gas diffuses, which is based on the speed of the particles, the speed of one gas compared to another gas is equal to the square root of the molar mass of the second one over the molar mass of the first one. What this essentially can be broken down to is big molecule go slow, right? And I don't mean to sound mean, but think about it in PE. Usually the bigger guys go run a little bit slower than the smaller guys go a little bit faster. They have less mass, so they're going to have more velocity. And if you think about it, this equation, it makes sense. If you're going to keep this constant and you increase the mass, well, you're going to have to slow down the velocity. And if you increase the velocity, you're going to have to slow down the mass. Okay, over here on the side are a couple examples of what's called Maxwell, Maxwell, something like that, distributions. And what they basically show us is the connection between speed and how many molecules are moving at that speed. So what we see here in this first one is that, like, helium, the lightest gas, its speed on average is a lot higher. Actually, I don't know if this one's a Maxwell-Boltzmann distribution, but I know the one below it is. But this still does show some connection between speed and the mass of these. So you'll see that, hey, helium, although it has a big spread of all these different speeds, in general, the average speed is much higher, assuming it's the same temperature. And our heaviest gas, xenon, the particles are much less kind of spread out in this distribution, and their average speed is a lot lower, which corresponds to its larger molar mass. So this can also be connected down here. This is for sure Maxwell-Boltzmann distribution, and it is somewhat common. I don't think it shows up every year, but it shows up frequently. And this basically, and it's going to be more related to kinetics, which we'll get into not next week, but the week after. This might be like activation energy over here. Okay, so what we see is as an element or a gas that has a greater average speed, so that's going to also correspond to a greater kinetic energy, so a higher temperature. Although it does have a larger distribution of where the molecules kind of are at, of what their speed is, the average is higher. And when we get to kinetics, we're going to see that you require a certain number of particles to be above what we call an activation energy for a reaction to occur. So in this situation where the temperature is a lot taller, and say like this marks the molecular speed, the energy required for the reaction to occur, with the hotter gas, you're going to have a lot more of the particles that are beyond the activation energy. So these are all basically concepts connected to KMT that you should be able to understand just by this idea that more energy, they're going faster. Gas particles, they're constantly moving around. We don't have to worry about the space they're taking up and all those kinds of things. This is also sort of connected to collision theory, which we'll cover in more detail when we go over kinetics. All right, next topic is deviation from ideal gas law. Well, before we can ask ourselves, like, because this is a really common question, is like, why didn't this gas behave the way we expected? Or they might show you a couple graphs and they say, which one is the more ideal gas? So first, we kind of skipped over what an ideal gas is. It's sort of connected to KMT, but essentially an ideal gas is assumed to have no volume. We don't want to assume any of the interaction we don't want to think that they take up any space. And it is sort of a good assumption because there is a lot of empty space in a gas, but it still matters. It takes up some volume. And there's no molecular attractions. That's the bigger one. There's no IM forces. Everything we learned at the beginning of this video, we're going to throw it out the window. And typically an ideal gas should behave the gas laws at all pressures and temperatures, which is going to be basically derived from the fact it has no volume and no IM forces. Now, a real gas has volume and has molecular attractions, and it actually experiences different behavior at low temperatures or at high pressures. Okay, pretty cool. So when they ask us questions like which one is going to behave least ideally, or which one's going to behave most like a real gas, or how come we predicted something's going to have 3 atmospheres of pressure, but when we measured it with a pressure gauge, it only had 2.8 atmospheres of pressure. Now, again, don't fight the data. Don't say, oh, well, your pressure gauge wasn't calibrated right. That's like the biggest cop-out ever. Unless they explicitly ask you to like, hey, tell us why this finding is wrong in like an FRQ, don't fight the data. So you have to think of a reason why. Like, how can you explain that disparity? And usually with gases, it has to do with it's behaving like a real gas. So now that we know what defines an ideal gas, if we want to know why it's deviating from ideal gas, means that it's breaking one of these 2 rules, no volume and no molecular attractions. Typically, this one is like this is like the trump card, the no molecular attractions. So usually we can attribute this difference to IM forces. For example, water vapor does have intermolecular forces. There's lots of space there, but sometimes those waters get kind of close to each other and they start to kind of clump up again because they do have that hydrogen bonding going on. Volume is also a factor, but it's sort of like second tier. The big one is going to be the IM forces that are present in real gases. Okay, up next is solutions and mixtures. Oh my, I hope I didn't miss anything. I feel like I've been trying to go fast after spending all that time on the IM forces. So let's see. What do you need to know for solutions and mixtures? Well, of course, you should know what a solvent is. You should know what a solute is, and that's when you put them together, you get your solution. So the solvent is what's doing the dissolving, and the solute is what's being dissolved in it. And a solution is, we talked about mixtures in, I think, one of the first videos. It's essentially a homogeneous mixture. Don't get me on the spelling. It basically means that it's evenly distributed all throughout the solution, the solute that's being dissolved. So it's not like there's a clump of it. Like if you put sand in water, that's not a solution. That's a heterogeneous mixture. All the sand's going to sit at the bottom. But a homogeneous mixture is going to be that it's evenly distributed all the way throughout. Now, in AP chemistry and high school chemistry, you're only going to be looking at water. So every single time your solvent's going to be water. If you go on and take organic chemistry in college or certain other types of chemistry, you're going to encounter other solvents, and they have lots of interesting properties and other uses. I was even just thinking today, like what kind of life would evolve if your solvent wasn't water, if it was like methane? It probably could lead to a whole different biochemistry. Pretty cool. But right now, you're just barely learning chemistry. We're going to focus just on water as our primary solvent. Some of the other concepts that go pretty well here is the idea of molarity, which is going to be moles over liters. There are some other ways to moles of solute over liters of solution. There are some other ways to represent concentration, which is how much solute is in a solvent, things like parts per million or molality, but those are all not on the AP exam. So don't stress out about it. Just be really good at understanding molarity. And hey, look, we got moles. So that means that there's probably going to be some stoichiometry problems connected to solutions. We're going to go more in depth in solutions when we get to the equilibrium and acid-base portion of the course, but you should know still the basics of it. Is there anything else I wanted to mention with this? I really don't think so. Okay, yeah, let's move on to the next section. The next section is the different ways that we can represent solutions. So we've got a couple of exclusion statements, and they say colligative properties will not be assessed on the AP exam. So that's basically what happens, how solutions affect melting point and boiling point. And the logic here is that that's apparently a basic chemistry concept you should have already learned before AP Chem. I don't know. Sometimes I read this College Board stuff and just scratch my head, but that's okay. And then we've got calculations of molality, percent by mass, and percent by volume will not be assessed on the AP exam. Okay. So all you need to know is molarity. Now, they love representing solutions with all kinds of different particle diagrams. So here's one example of kind of explaining how a solution forms. So the solute, if it's going to dissolve in the solvent, it has to essentially expand, and that's going to require energy. So it requires some energy. And same thing over here, the solvent as well is going to need to use some energy. This might be called like enthalpy of dissociation or something, to expand as well. And then they're able to come together and they're able to kind of mix themselves like all the way through. Particle diagrams, AP loves particle diagrams because it allows them to see if you understand how to talk about the microscopic interactions and you didn't just memorize a bunch of macroscopic facts. They want to know that you can connect the two domains. They constantly love to see connections. So they love micro to macro connections. And the other thing I've noticed they really like, it's not so much in this unit, but they love connecting theoretical to like experimental stuff. That's why they love PES spectrums and other types of like lab experiments that connect these highly theoretical concepts to actual tangible data. Okay, so I threw this one in here because I like this question and it's time for a little bit of practice. And this is like an idea of what these look like. So a student mixes a solution of lead nitrate with an excess amount of potassium iodide, and a precipitate of lead iodine is formed. Which of the following particle diagrams accurately represents the major ionic species remaining in the solution after the reaction has been completed? Okay, so the lead, we had a certain amount of lead and a lot of excess. So think of excess limiting reactant like stoichiometry and lots of Ki. So right off the bat, I'm going to expect to see some Ki floating around, which I don't see in all of them. I don't see it here, but I would expect some Ki to be floating around. And some of the other I in lead is going to create this solid substance. And since we have excess Ki, that probably means all the lead is going to be consumed in this reaction. So I don't want to see any lead floating around in solution, and I don't. Now, what's going to happen to this nitrate? Nitrate's going to dissociate from the lead as it binds with iodine, and it's going to at least temporarily form this compound, KNO3. The next thing we're going to talk about is solubility. If you know your solubility, you'll know that KNO3, they don't like to stick around together very much. Also, we do have a little bit of extra I in the mix too. So I'm not going to choose this one because it has no iodine. So I'm down to the last two. Now, the ratios is where they're getting you here. So for every lead, you have 2 nitrates. Okay, so I would expect to have, I would say, well, I guess we don't know the lead. Sometimes you gotta scratch your head on these. Oh, okay. So I think that this one's probably better. And if you notice, we have 4 potassiums floating around and only 2 iodine. However, they came all in this original potassium iodine, so you'd expect to have equal amounts. But aha, some of that iodine bonded with the lead to form the precipitate at the bottom. So I like this one because it has more potassium than iodine. The one over here has more iodine than potassium, which doesn't really make sense because the ratio from potassium to iodine started as 1 to 1 since the compound was Ki, and some of that iodine went and started a new life with lead. So this is probably the best choice. This is the kind of questions they love to ask. It's not just about what dissolves. It's, can you think about the stoichiometric ratios? Can you think about what's soluble and not soluble? And can you choose a reasonable particle diagram? Okay, moving forward, separation of solutions and mixtures chromatography. Oh, all right. So way back in our first video, we did briefly mention mixtures and like sort of what defines them versus a pure substance. And mixtures can be physically separated, whereas a compound, a pure substance of a compound cannot. You cannot separate hydrogen and oxygen from water by just boiling it. You have to do a chemical reaction to do that. So mixtures can be separated by physical means. Now, a heterogeneous mixture you can separate with filtration, right? Like, which is like when you're a kid, you put like sand and water through like a sieve, and all the sand will get trapped and the water goes out. When you make pasta, I guess that's technically a mixture, right? You got chunks of pasta floating around, pasta water. You pour it through your colander, and the pasta stays in there, and the water comes out. But for solutions, which are homogeneous substances, you cannot use filtration because it's all evenly out there. You would need a filter with pores the size of atoms, which I don't know, maybe it does exist, but it's not going to typically exist in the laboratory. So we have these 2 main methods of separating mixtures. The first one's called distillation. Second one's called chromatography. And they both rely on the idea that there are different physical properties in the 2 substances you're trying to separate. So for distillation, you might have 2 different substances with different boiling points. And what you do is you boil the entire thing at a certain temperature, and it's going to evaporate. The one with the lower boiling point is going to evaporate, and it's going to go up here, and then it goes down into this condenser. And this is like you might see in like old cartoons, sometimes these condensers, they draw them as like this big curly thing. That's just giving it more chance to essentially cool off so it can recondense and form back into its liquid form. Meanwhile, this substance with the higher melting point is still going to be left over. This is essentially how they distill hard alcohol. And then during the bootlegging days, when alcohol was illegal in the United States, they would use this process, and they'd kind of not be doing it like up to par. And there's another side chemical that's also created in fermentation sometimes, which is methanol, wood alcohol. And it can be very lethal or damaging to the human body. And the problem is, if they didn't have that boiling point just right, some of that methanol could actually get mixed in with the ethanol that they were essentially trying to isolate. They would try to evaporate them and separate them. But if you're doing this bootleg in your bathtub, doesn't always pan out that way. So distillation, you use boiling points to separate a mixture. One will evaporate out first, and the second one will be left behind, and then you can recondense the one that evaporated. The second concept here is chromatography. Now, a lot of times you do this either in high school AP Chem, or you've done it before in middle school or something. And this is essentially using differences in polarity. So essentially, the example they often use is markers, because markers usually use, instead of black ink, they usually have like a mixture of colored inks that appears black. So you could put some black ink, the solvent, whatever it is, kind of moves up the paper. And the ink has one of 2 choices. It can either dissolve with the solvent if it has a similar polarity, and it will dissolve with the solvent and it will kind of move up the paper. Or it could be more attracted to the paper and it won't move very far at all. So this is all going to depend on this idea of like dissolves like. So if the solvent is polar and the substance is polar, then it's going to move along with it. If the solvent is nonpolar and the substance is nonpolar, it's going to move along with it. So do read it carefully. Sometimes they do give examples where the solvent is polar or nonpolar, or they might tell you the paper is polar or nonpolar. So think about all that. Another important concept here is the solvent front. It's not so much of just how far the substance moved, especially if you're doing multiple multiple tests with different solvent fronts. It's about how far it moved relative to the solvent front. So if you moved halfway, so this one's not halfway, this one's what, 6 centimeters, we would say this has a retention factor. That makes me how much did the solvent retain that ink of about 0.6. And that's what's really going to allow us to compare the polarities and stuff like that. Now, this isn't as useful of separation because you can't like actually have it at the end. It's just a little bit that you're testing. But it is still good at being able to show differences in compounds. Now, this isn't only used for markers. That's the example they always use in class. But chromatography is used in all kinds of applications. If you go to college, organic chemistry, like every lab, you're going to have to use chromatography to show if the substance is what you thought it was. It's one way of showing like, oh, I thought I distilled a polar substance, and yeah, it actually behaves like a polar substance. So these are the two main ways that you need to know of separating solutions: distillation, this lab technique, and I think I'm going to try and make a lab technique video towards the end of the series, and chromatography, which separates it more based on polarity. If you still don't get these and you want some practice, I have some really good practice questions and worksheets that I can help you with as well. All right, so solubility. So this used to be a real pain in the butt. Like when I learned chemistry in high school, like there was this big old list you had to memorize of the solubility rules. And I had no idea why I was memorizing it. It seemed sort of arbitrary. I did not understand it had to do with like charges or positive and negative or anything like that. So you don't have to memorize all these solubility rules of what dissolves and what doesn't anymore in AP chemistry. They decided that these are the ones that AP Chem wants you to know. Sodium, potassium, ammonium, and nitrate always dissociate, which means the ions separate when they're in water. Also, most of the other alkali metals are going to separate as well. A lot of the hydroxides of many of the alkaline earth metals will. Some things like carbonates and sulfates tend to not dissolve, but you don't have to know that. They said they want students to have a better understanding of KSP, which we're not going to talk about today. That's going to be for this super epic acid base video that's coming someday. Another thing you should know is that strong acids and strong bases, they also fully dissociate in water. The concept that AP really wants you to know is that like dissolves like polar dissolves polar, nonpolar dissolves nonpolar, but you can't say that in your explanation, right? Like if you say like dissolves like, you're not going to get the full points on an explanation. You need to say something about like they have similar intermolecular forces due to their polarity. Okay, so be careful there. But yeah, there's not much to say about solubility since you don't really have to memorize as much anymore. You do need to understand what it means, which is that the particles are going to come apart. And when we get to the acids and bases and this whole solubility product thing, we're going to see that actually everything is a little bit soluble in water. It's just what the degree is. And we're going to learn that KSP can actually tell you how soluble something is in water. But that's like a whole nother conversation for another day. Okay, let's keep this thing going. Spectroscopy and the electromagnetic spectrum. Okay, so here's our electromagnetic spectrum. So now we're like, dude, where did this come from? And it's very applicable to a couple of experimental techniques. And I did tell you that they love connecting experimental techniques to theoretical techniques because it shows that you really get the concepts, that it's big and small, that it's theoretical and it's experimental and everything connects. It's not two different fields of science. It's all represented by chemistry. So spectroscopy and the electromagnetic spectrum, I teach about this in biology. I teach this in chemistry. I teach this in physics. I teach this in regular level science. I feel like you should know it by now. But if you don't, radio waves are on one end and they have very long wavelengths. They're so big that they're just going through your body all the time and you're not even noticing it. Same thing with like a Wi-Fi and microwaves as well. Infrared, which is also known as heat, is light that is of larger wavelength than red light. And also, along with these longer wavelengths, they also have a lower frequency, which is how often their wave kind of goes through a cycle. And they also have lower energy. So this is big wavelength, and then it's small frequency. They use this symbol for some reason, so new symbol. And they also have small energy. And as you move down the electromagnetic spectrum from radio wave to microwave to infrared to visible, and if you notice how small visible is, so what we call light, what we can actually see, is a very, very, very small piece of it. That if we get all the way from red, all the way past violet, then it becomes ultraviolet. That's the light everyone's telling you is bad for your skin. And it is, because it's a lot higher energy and a lot shorter wavelength. It's much easier for it to penetrate through your cells and mess with your DNA and cause cancer. And as we get a little bit higher, we get to X-rays. These are really high energy. Now you know why the X-ray technician puts on like a hole on, like standing outside the room and covers your body with lead, little lead apron. And then as you keep going, you get up to gamma rays and cosmic rays, which are flying through space. And they're super, super high energy, very, very short wavelength. They kind of just penetrate everything. Now, there's all kinds of other things you can talk about here, like particle wave duality and all these cool quantum concepts, but they're not on the AP exam. So if that stuff interests you, go ahead, check it out. It's probably in your textbook. And it's definitely worth learning about. It's very fascinating, but it's not on this test. So I don't even know if they would ask you directly about the electromagnetic spectrum, but there are some things you should know. The first one is, what do these types of radiation do to molecules? And microwaves, and honestly, I did not even know this. I was in teaching chemistry. I studied chemistry, and I learned this year. So there's always something new to learn. Microwaves, what they do is it's associated with transitions in molecular rotational levels. So it's affecting the way the molecules are rotating and oriented, which is actually why microwaves heat up your food, because those water molecules start spinning so fast that they actually generate enough heat that they can warm up your food. If you try to put a piece of beef jerky that has no water in it, or like a dried apple piece or a banana chip, it's not going to get very hot because there's not enough water to really get revved up by the microwave. Infrared radiation is associated with transition in molecular vibrational levels. Sometimes this is like, I've seen it talked about as like bending and stretching of bonds. I didn't even know that was possible until I learned about it recently. So yeah, know that. And finally, ultraviolet and visible radiation. These are the ones that we usually learn and teach about, which is they can actually cause transitions in energy levels in an atom. They are just the right amount of energy that it can excite an electron to jump up a level in its orbitals, and as it falls back down, it's going to emit a photon. All right, next up is the photoelectric effect. So again, this is just so you sort of understand it. Oh, also, usually visible light is measured in nanometers, which is equal to 1 × 10⁻⁹ meters. So just be careful when you're reading through stuff. Is it asking it for nanometers? Are they expecting you to use meters? Most of the calculations we're going to look in the next couple slides, you need to use it in meters, though they often will say something like, oh, it's a light with a wavelength of 450 nanometers, which is somewhere, I think, in like the greenish area. I'm not 100% sure off the top of my head, but just be aware that that's a common unit that's used, even though in the calculation you probably need to use that one. Also, there's a connection here: big wavelength, small energy. Small wavelength on this side, like these little tiny waves, and this is going to be a big energy. Okay. All right. So the photoelectric effect. This is not exactly the photoelectric effect, but it's sort of connected to it, the one in the top left. And this is maybe the one you're more familiar with. So this is when energy is absorbed from whatever place. This could be kinetic energy. This could be radiation. This could be lots of different things. But the perfect amount of energy comes in, and it's just enough to excite this electron to jump up to the next energy level. Because the energy levels of an atom are quantized, and each atom, not just each atom, each molecule has its own kind of energy levels with its own quanta, different amounts of light is going to cause this electron to jump, or different amounts of energy. And then when that electron jumps, well, it can't stay there forever. Eventually, it's going to fall back down. And when it does so, right here, when this electron falls back down, it goes from a higher energy to a lower energy. So there's a change in energy. Energy cannot be created or destroyed, so it gets emitted, usually in the form of a photon. Each of these transitions between different energy levels has a different amount of energy associated with it, and therefore emits particles of different energies. If the energy corresponds, and we'll see how we can connect it to a specific wavelength that we can see, we will actually see light coming out of it. And this is why probably one of the most fun labs is like the flame test lab, right? If you've got to do that in chemistry or maybe in an introductory chemistry course where you burn different salts and they create different colored flames. And that's how they make different colored fireworks. That's how those a lot of lights are changing to LED, but the classic street lights with that orange color, that's actually sodium lamp. And it's using sodium. The emission from sodium is that yellowish orange color. Okay, so the same equation is going to apply for this, which is essentially these jumps in different levels in the atom, and the photoelectric effect, which is if you shoot light at the right wavelength with the right energy at certain at any substance, and if you get it just right, it can actually cause an electron to jump out. It's enough energy so that it makes it out of there. So we call this the photoelectric effect as well. That's using just the right amount of energy to actually get the electron to get so excited that it leaps out. Of course, that's going to be different for different atoms. Again, they really like this concept because it allows us to visually take all of our weird models of the atom that we don't really know. Like we can't see it. Like I guess we know it, but we can't really see it. And it starts to verify some of that stuff. All right, so the big equations that you want to know in order to essentially solve questions that are related to this are these right here. The energy of a photon. A photon is one little packet of light. I know we say, oh, isn't light a wave? Let's not get into the whole wave particle duality, but it means little packet of light, little particle of light. Light can be described as a particle equals something called Planck's constant times this, which is frequency. Ooh. Again, frequency is how often the wave is going through its cycle of up, down, up, down, up, down. There's another connection, which is c, which is the speed of light. Now, I usually tell people it's 3.0 times 10 to the negative 8 or the 10 to the 8th, but you probably want to look it up. It's probably maybe it's 2.99, 2.88. I don't know what AP is using on their formula sheet. Probably something pretty accurate, though. Meters per second. And it's equal to the wavelength. That's what this weird symbol is. So how long the wave is from peak to peak or trough to trough, and then also the frequency. So if you ever get lost when you're trying to do calculations on the AP exam and you see that there are two formulas with the same variable, that's like, oh my gosh, this is so amazing. We can now set them equal to each other. So E over H equals C over lambda, and we can do whatever we want with that. If we know the energy, we can go straight to finding the wavelength. If you don't like doing it that way, you could use the energy to find the frequency and then plug that into the equation. Doesn't really matter, but whenever you notice in these kind of things that you have equations with the same variable, multiple different equations with same variable, it's showing you there's a bridge there. There's going to be a connection here. One that's really common is moles, right? They're going to allow you to connect lots of different things. That's why I said the gas law gets connected to all kinds of stuff because there's all kinds of variables in that one. Finally, this letter H is called Planck's constant, 6.626 times 10 to the negative 34th joule seconds. Don't worry about the units. Most of these constants have really weird units. It's just to kind of cancel out the other units so that you get what you want. That's how I always look at it. But this is given on the AP exam, so you don't have to memorize that. I'm pretty sure they give you the speed of light as well, and they give you both of these equations. So in this case, we could say something like, oh, 550 nanometers light was used to eject the electron. Cool. And we might say, what was the energy that electron had, and you could calculate it using that. Or in this case, oh, they're even finding the velocity, so they might be able to tie that back into like the k equals 1/2 mv squared equation. So whenever you see these equations, don't just think they're something to memorize and do math with. They can also help you connect different concepts together. Oh, that's the photoelectric effect, though. Woohoo, we're almost done. The last one on here, and you can tell this chapter, it seems like they just start throwing random crap in there at the end. This is called the Beer-Lambert Law. I'm pretty sure most of you guys have done a lab about this. If you haven't, I would watch some kind of YouTube video that goes into more detail about the actual lab. Now, this is the equation they give you on the AP exam. I've seen it written in a lot of places online as ABC. I don't know why they do that, if this is the more common form. And look, even this one that I found online is using AELC. Whatever it is, whatever form, it doesn't really matter. It just matters what they stand for. So A is a measure of the absorbance, which is how much light a solution is going to absorb. Okay, and it's based on the molar absorptivity constant, which is something unique to that specific material. So usually when we use Beer-Lambert law, we use a liquid that has some kind of color to it. So it's usually going to be based on that, like how absorptive of this specific light is that going to be. And then L is the length of path traveled by the light, and C is the concentration in molarity. Now, this is all based on a specific frequency of light or wavelength of light that you determined before. I'm not going to get into that of how you choose which wavelength of light you want to use and what the intensity is and those kind of things. But this is the general equation you're going to use for the Beer-Lambert law. So real quick, what is going on in the Beer-Lambert law? So you have light coming through, and it's getting some of it might be getting kind of absorbed or diffracted or whatever, and only a little bit of it gets transmitted. Like, I thought this was about absorbance. Yeah, it is. But we kind of measure it sort of backwards. So transmittance, how much actually gets through, is sort of inversely related to absorption. So the more that's absorbed, the less that's transmitted. Now let's think about those different variables that were involved. So this is the actual substance, like the particular molar absorptivity of the substance. So sometimes you might be trying to calculate that. Sometimes it might be given. But it's going to, or you might be like have calibrated the machine ahead of time about that. But it's basically going to be based on what it is you're shining through. If you're shining through a clear liquid, then this number is not going to be very big, right? Because it's not really affecting the absorbance very much. This is based on the length. So the longer distance it's going through, the more chance some of the light's going to scatter and be absorbed by the solution. Usually we use 1 centimeter in the lab, although technically I guess you could use different sizes. And then this is finally the concentration of the material. So the more concentrated it is, the more particles you have in your solute, the more chance that they're going to disrupt the light from going through. So we can graph this data in terms of absorbance versus concentration. And this is usually what we use this for. We calibrate it with a couple different known concentrations, and then we can take an unknown, like maybe we got these data points from known concentrations, and then we throw in an unknown and it pops up somewhere. The concentration is like right here. So, or I mean, that's not how we would measure it. It would give us a readout of absorbance. So maybe it says, oh, the absorbance is about 0.9. So we could use this graph to say, oh, I bet you that the concentration is a little bit less than 0.6. So that's usually the application of it. There is a lot more to Beer's law. I haven't seen them. They don't ask like that many questions about it. If you just sort of understand the equation and how to essentially use the data, then I think you're okay. But they haven't used it in a while. Might mean that they're going to ask you a question on it soon. So at least go back and make sure you understand your lab. That's going to be able to connect a lot of the ideas together for you. And I think that's it. Yeah, we made it. Woohoo! Okay, so great job for hanging in there. If you watched the whole thing, I know that was quite a bit of talking for me. I thought it was going to go longer when I saw all those topics, but I guess it didn't. So hopefully you found this video helpful, or at least a little chapter or two of it. If you did find it helpful, please like and subscribe. If you didn't, I'm always open for feedback, so let me know what would have been more helpful. Of course, if any of these concepts you're still really struggling with and you could use a little bit of extra help, I am here to support you guys in any way possible, whether I know you or don't know you. And I want to be able to help you at the individual level. So if you need a little bit of extra help, if you needed some direction to check out some other videos or check out some good worksheets or websites or practice problems, or even if you just need a little bit one-on-one help, reach out to me. I'd be more than happy to help you. And with that, happy studying. We got only a few more weeks left, so I hope you're buckling down and stick to it. All right, have a great night.